In this video, we provide an overview of BERT, or Bidirectional Encoder, Representations from Transformers, and GPT, or Generative Pre-trained Transformer. As a reminder, tokens can be words, punctuation marks, or subword units. A vector represents the numerical value or representations of a token. In NLP, tokens are typically represented as vectors. So tokens are the smallest unit of text, and vectors represent their numerical values or representation in NLP. By converting text into vectors, we can then use mathematical operations and machine learning algorithms to analyze and manipulate them. This is a diagram of a transformer, a neural network architecture used in natural language processing. The transformer is made up of two parts, an encoder and a decoder. The encoder takes a sequence of input data, such as a sentence in a language, and converts it into a sequence of vectors. To preserve the positional information of words in the input sequence, transformers incorporate positional encoding vectors. These vectors provide information about the position of each word in the sequence and are added to the word embeddings before feeding them into the transformer layers. This ensures that the transformer can distinguish between words based on their position in the sequence. The core of the encoder neural network consists of multiple identical layers of transformer blocks. Each transformer block typically includes two main subcomponents, the self-attention mechanism and the feed-forward neural network. The self-attention mechanism allows each token in the sequence to attend to all other tokens, capturing dependencies and relationships between words at different positions in the sequence. Let's look at an example. First, we get a token representation of I love NLP. Then the I in I love NLP attending to itself and the love and the NLP is calculated. The attention score for I is then 1, 0, 0. The same calculations are done for love and NLP, where each token attends to itself. So here the attention score for love is 0, 1, 0, and for NLP 0, 0, 1. This representation of attention scores and input embeddings is more aligned with how they would be used within a transformer neural network, as they are typically used as weights to compute a weighted sum of the input embeddings, producing context-aware representations for each token in the sequence. In this example, we first define the attention scores and input embeddings as PyTorch sensors. We then use PyTorch's torch.matmul function to compute the weighted sum of input embeddings based on the attention scores. The resulting context-aware representations tensor contains the context-aware representations for each token in the sequence, which can then be fed into the subsequent layers of a transformer model. These scores indicate that each word has full attention on itself and no attention on the other words in the sequence. But what about a case where there are unequal weights in the sequence? The self-attention mechanism in the transformer neural network enables the model to determine unequal weights among words in a sequence by dynamically adjusting the attention weights based on the context and relationships between words in the input sequence. This allows the model to capture fine-grained dependencies and extract meaningful representations from the input data. From the attention scores in the second example, we can see that books has the highest attention score, 1.0, when attending to I, enjoy, and reading. Therefore, books receives the most attention in this example, indicating that it has the highest weight or importance in the sequence. The high attention on books implies that it may have a strong influence on the predictions made by the model. In tasks like machine translation, for instance, the attention on books could affect the translation of the entire sentence, especially if the word carries essential semantic or contextual information. After applying self-attention, the contextualized representations are passed through a feed-forward neural network, typically a multi-layered perceptron. The feed-forward neural network applies nonlinear transformations to the contextualized representations, the "I enjoy reading books," and enables the model to capture complex patterns and relationships in the data. Both the self-attention mechanism and the feed-forward neural networks are followed by layer normalization and residual connections. Layer normalization and residual connections work together to stabilize the training process and ensure efficient information flow through the network. The decoder then takes the sequence of vectors and converts it back into a sequence of output data, such as a translation of the sentence into another language.